So hello everyone. So let us start our new session. Basically, in the last session, we have started the magnetic field and we have seen the magnetic field due to the different geometries. We have seen the infinite long wire, then semi-infinite long wire, then finite length wire, and then we have talked about the circular ring also, and we have calculated the formula for that also. Then we have take the general case of the ring also, and we have calculated the formula for that also. All these things we have done, and we have done a lot of illustrations on. Now in this session we are going to start with the magnetic field on the axis of the ring, and we are going to proceed this discussion more further. Okay. So before that I have given a one homework question. I hope everyone has solved this. So basically, so let us see the solution for this. The solution is very simple. If you are able to understand, we have to do only one thing. What? Because in this case we have to do a simple approach. What is a simple approach? Obviously you have to integrate because it's not a linear case. So what we will do, from a center x, we will go and we will take a small element. Correct? Any doubt? We will take a small element whose thickness will be what? Whose thickness will be dx. Correct? Whose thickness will be dx. That is what we used to do. Correct? Now this is the same thing we are going everywhere. Whose thickness is dx. Obviously, then my thing is that what is the formula for magnetic field? What is the formula for magnetic field? Because it is a small ring. And what is the magnetic field due to the small ring? Tell me, what is the magnetic field due to a very small ring? What is the formula? If I am writing a magnetic field due to a small ring, what is the formula? If you have remember, I told you the formula in the last class. What is the magnetic field due to the small ring? Tell me, what is the magnetic field? Mu naught I divided by 2. What is the radius? Is x. What is the total number of turns? Total number of turns. Because see, I is not exactly I, basically it's or you can say like let me try to explain you. See, what is the total number of current? The total current will be in this, suppose basically the total current is I here, that is given. The total current is I here, that is given, and that is the total current in n turns. Means what I am trying to say is I is a current which is present in n turns. Correct? That is the total current which is present in n turns. But my question is now, I have to calculate current in this number of turns, in this small element. How many turns? What is the current in that? So for calculating the current, it is not I, obviously. For calculating the current in that, what I have to do? See, I current is present in n turns. If I know how many turns are there, can I calculate the current? Correct, obviously. So I can say, see, n turns are present in b minus a width. In b minus a width, how many turns are there? N turns. Correct? So in dx width, how many or you can say dx width, in this number of bits, how many turns are there? That will be n upon b minus a into dx. Correct or not? This much only. Are you getting my point? This number of turns are present. What I am trying to say, in dx width, the number of turns is how much? Dx into capital N upon b minus a. And what is the current? I current in n turns. So n turns is equivalent to I current. So we can say dx into n divided by b minus a will have how much current? I dx into b minus a into n. This much amount of current should have. So now just put the value. You will get I n into dx into b minus a. Simple. This is the thing we will get. Now we have to integrate simply from a to b. So when you integrate, you will get mu naught I into n into 2 into b minus a into integration of ln b by a. And what is the value? This is inside, that we know by the hand. If you curl, you will get inside, sorry, outside, not inside, it will be outside. Okay, that is a very famous question of previous year question. Okay, so just as every institute used to solve this, so I also given you the idea. Basically, it's a only question by which you can understand the application of a good application of a magnetic field at the center due to the circular coil. That is a very good application of this. Clear? It is a very good application of that. Now next thing we are going to talk about is something called magnetic field. Magnetic field on the axis of circular ring. We have talked about the center, but now we have to discuss about the circular ring. So let us start our discussion for a circular ring. Correct? So first you tell me one thing. For a circular ring, if I am talking about at the axis, some point at the axis, what I am trying to say, just try to understand the situation now. The situation is now like this. You have a ring and I am saying you to calculate the magnetic field at some distance from the center. Suppose the distance is x. From the x distance from the center, this is a point which is called center, and this radius is r obviously, and I am going to calculate the magnetic field at this point, and the current is going like this. Okay, the current is like this. So at this point, if I ask you magnetic field, how will you calculate? Keep your thumb in the direction of that and then curl your finger. So if you do this, you will get the magnetic field in this direction. Correct? Just you can see this also. Thumb is pointing in this. Basically, what is the rule? Just keep your thumb in the direction of current and just curl your finger where the point you have to find the magnetic field. So if you keep like, see, it is like this. So if I keep my thumb like this and I curl my hand, so it is going inside now. It is going inside. So magnetic field will be like this. So that is clear. Magnetic field is like this. This is my direction of magnetic field. Okay, no issue. But I have to calculate its value. How I will calculate? Simple approach. We know how to take the element in the ring that we have discussed in electrostat. See, if I take a small element, what I will do, I will take a very small element here who's having a length that is dx. Okay, correct? A small element having a length dx. So due to this, the magnetic field will be, what is the direction of magnetic field? Well, first you tell me, what is the direction of the magnetic field? How the magnetic field, what is the direction of the magnetic field? My simple question is that, what is the direction? See, this is my I vector. Try to understand. This is my I vector, this is my R vector. So I cross R, DL cross R, or you can say I cross R. So DL cross R is coming like this. Okay, see, like try to understand. See, this is my ring. The current is going like this. Okay, current is going like this. Okay, current is going. I keep my thumb in the direction of this, and I keep at the point R. And what is the formula? DL cross R. So DL is like this, or you can see, you can keep like this. DL cross R. DL cross R means I have to turn toward this direction. DL cross R. So it will be something like this. So the direction of magnetic field will be in downward direction, but then I think we can do one thing. In spite of making it downward, we can do one thing so that it will come. Other downward I can do, but just to make the derivation little easier, we can do one thing. We can take the current direction like this. I'm just reversing, it doesn't matter. Okay, I'm just reversing the current direction so that the everything will be, so calculation will be more easier for us. Otherwise we have to take the element in opposite direction to solve it properly. Okay, this is a current and this is my radius R. What I'm saying, at this point you have to find this distance is x. Okay, so at this point you have to find the magnetic field. Correct? Simple way is what is a simple method to do this? First you have to DL cross R. Just start doing first you have to find the direction of the magnetic field at this point. Okay, that is my simple approach. And suppose this distance is x, not x, because x we have taken. Suppose this is a small r. My question is, and suppose this angle is theta. I don't know anything. I just know that is the direction of, by Biot-Savart law, the direction should be, what is DL cross R. DL is what? See, this is the ring and the current is going like this. Okay, current is going like this. So DL, that is my rule. DL means my thumb in the direction, or I have to put my fingers in the direction of one vector, DL cross R. Cross R means I have to curl toward this, means the point is here na. This is my ring. So DL cross R means my DL should be like this, and I have to curl toward this. DL cross R, DL cross R, DL cross R, like that. Okay, or you can say I will I will put my thumb in the direction and then I will do dl cross r. I will put the thumb in my that direction. I will do dl cross r, dl cross r. Thumb in the direction, dl cross r, dl cross r, dl cross r. What is the direction? It is going like this. It is going like this. Okay. Again, try to listen. Suppose this is my ring. I am putting my. See, there are two methods. First method is put the finger in the direction of dl. dl. This is my dl vector. And what is the rule? Dl cross r. What is the r point? The r point is here. So dl cross r, you have to turn toward this. Dl cross r, dl cross r. It is coming upward like this. It is coming upward direction. Simple. Another method is what? Put your thumb in the direction. Okay. Then dl cross r. Put your thumb in the direction of current and dl cross r, dl cross r, dl cross r, dl cross r like this. Again, you are getting in this direction. The magnetic field will be in this direction. We are getting correct. Okay, so this angle is theta, this angle will be 90, correct? So what is this angle? Because it is perpendicular to both the vectors, correct? So what is this angle? You tell me. This angle is 90, okay? This angle will be 90. Now what is this angle? Theta 90, then it is how much? Total angle is 180, so 180 minus 90 minus theta. How much? It will be 90 minus theta, correct? This is 90 minus theta. Any doubt till here? Okay. If I take the another element from here, in this case, the direction will be like this, correct or not? So this will be cancelled out. So if I take the two components of this, one horizontal and one vertical. So what is the horizontal component? The horizontal component will be come out to be dB. dB cos 90 minus theta sin theta, and dB sin 90 minus theta is equal to cos theta. So this is dB cos theta, correct? And this is dB sin theta. And dB cos theta and dB cos theta is 0. Why? Because of the symmetry. Because of symmetry. And now you understand how it is 0. Because why? Because we have discussed this in electrostat. Because of symmetry. Because why symmetry? Let me tell you why symmetry. Why symmetry? Because simply, if you take the element for this part, you will get the magnetic field in this direction, correct? Then you will take cos component, sin component, this will cancel out. Simple. That is why it is coming 0. Okay, is 0. Okay, so that's why, if you remember, initially I told you, if you curl your finger, the direction in which the thumb point is the direction of net magnetic field. So our net magnetic field is outside only. That is what I am telling. Okay, and that what we are doing by this, we are calculating a magnetic field due to that small element only. We are not talking about when I am doing this thing by when I am curling the finger around the current direction, then I am calculating the net magnetic field. This is giving the direction of net magnetic field. And when I am putting A cross B, I am doing, then I am calculating a magnetic field due to that small element. Okay, so take care of these things. That things are very important. That is why physics is little difficult for you, because you are not listening to the each and every point. You have to be clear with each and every point. Then only you can understand. So the dB cos theta, because of the symmetry, is 0. So our B net will be is along the axis. Along the axis. It will be along the axis. Clear? So if it is along the axis, so let my B net is equal to how much? Integration of dB sin theta. Correct? Yeah, dB sin theta. Now, now simply, what is dB? First tell me what is dB. dB is simply defined as mu naught I by 4 pi, correct? Now you have to write the other values. What is that small element is? We have taken a small element. What is that small element? It is a small element. There you can take it as dl. Okay, that is a small element. Mu naught I dl. Then what is the angle between the dl vector and r vector? That is an important question. What is the angle between the dl vector and r vector? Obviously 90 degree. Yes or no? This thing we have done the study 1 derivation. We have seen for a ring derivation, because this is my dl vector and that is my r vector. So what is the angle? 90 degree, you can see. Okay. So this is sine 90 divided by what is the distance? This is r. R square is the distance. Correct. So you will get mu naught I di into 4 pi r square. Just put this value here. You will get integration mu naught I dl 4 pi r square. What is sin theta? Sin theta is how much? Sin theta is how much? This is r upon under root of r square plus x square. Array, this is what, how much, r square plus x square, correct now? And what is this value will become? Mu naught I into r divided by 4 pi r x square plus r square to the whole power 3 by 2, correct? And then you have to integrate dl. What is the integration of dl from 0 to 2 pi capital R? So what is the value you will get? Mu naught I into r square upon 2 into x square का whole r square power 3 by 2. That is my B net. And what is the direction? Along the axis. Along the axis. How will you find the direction? The rule is very simple. For this, curl the finger in direction of current, and thumb will give the direction of B. Correct? Simple. Just curl the finger in the direction, thumb will give the direction of a B. Clear? That is a formula which you have to remember. See, in this case, if I ask you one thing here, let me ask you whether let's see whether you are able to tell or not. This is visible? Okay. So let me ask you one thing. What is if my x is equal to 0, then my B will become at center, correct? What is the magnetic field at center you are getting? Mu naught I by 2r. Yes or no? This is what we have calculated earlier also. When x is equal to plus or minus infinity, what is my magnetic field at this point? What is the value you are getting? 0. So can you tell me what is a graph will look like? If I draw the graph for this, can you comment about the graph, how it will be look like? Are you able to comment on the graph, how it will be look like? See, you have to be, your approach should be mathematical, then you will understand the things in better way. You have to be little mathematical. Okay, obviously it will be something like this. Okay, at center it is maximum, at center it will be maximum, and then it is start decreasing. At center it is maximum, and then it is start decreasing. So at center it has a maximum value, this is B at center, and then it is decreases. This is magnetic field vector versus x, correct? This is how the graph will look like. So everything we have done for the magnetic field at the axis of the circular ring. Just remember this formula because this is very important, and you have to remember the graph for this. And we have solved the different examples also. So let us, I told you also one thing, for the next class you just revise all the electric field properties, because these properties we are going to similar manner we are going to discuss about the magnetic field properties. So let us put a new heading, that is properties of a magnetic field lines. Before that, I would like to tell you something about the magnet. Basically, as we in electrostat, as we have seen something called as a dipole. If you are able to remember, we have seen something called as a dipole. Similarly, here also in magnets, magnet, in electrostat we have seen a dipole and we have talked about dipole moment. In magnet we have called magnetic moment, magnetic dipole. We have something called as a magnetic dipole and magnetic moment. So let's take a look what is that, and then we will move toward the properties of a magnetic field lines. Because this is going to become there, so that's why it is important to let's take a look of this. Basically, you know bar magnet. This is what our bar magnet, correct? This is a bar magnet, which we know everyone. I think everyone know about the bar magnet. Everyone have seen also what a bar magnet is. Suppose this is my bar magnet. Okay. So if it is a bar magnet, we know there is a two poles are there. What are those poles? One is a north pole and one is a south pole. Basically, we try to build an analogy with electrostats and the magnetostats or magnetism. We try to build an analogy whenever we study about the dipole. Basically, what they used to say, the electric dipole is exactly same as that of a magnetic dipole. Just replace the north pole by plus q and south pole by minus q. Simple is that. Just what you have to do, you have to replace the north pole by plus q and south pole by minus q. Basically what that is an analogy, and all the formula, everything will be exactly same just by replacing the north pole by plus q and south pole by minus q. That is called as an analogy. Okay, so slight difference are there that we will tell you, and that will come in later, but just for now, sake of convenience, I am telling, suppose this is my bar magnet, so that will act as a plus q. This is going to be act as a plus q, and this is going to be act as a minus q. So for here, and suppose the distance is, I am taking as 2l. So here we define something called as a magnetic moment. Magnetic, this is called as a first, this is called as a magnetic dipole. Okay, this is the magnetic dipole. Okay, this is a magnetic dipole. Okay, and magnetic moment is equal to, like the dipole moment. What is a method? See, here we define something called as a, see, there are the two poles are there na. So for that poles we have defined something called as a, this, for this we have a something called plus m, okay, in terms of magnet, and for this we have something called minus m, where m is what? M is termed as a pole strength. Like q has a some charge na, it is a some charge, treat it like that only. Okay, so it is a pole strength whose value will be given to you. Okay, pole strength. So if I want to define my magnetic moment, what I will do, I will write pole strength into distance between them, that is 2l. And as it is a vector quantity, so what is the direction? See, in the electric dipole movement, electric dipole, we have seen that direction is from negative to positive. We have seen that the direction is from negative to positive. So in the magnetic also, the direction is from negative to positive. So what is negative? That is south pole. What is positive? That is north pole. So what is the direction if I ask you? What is the direction if I ask you? Direction is from south to north. South to north. So that much you should remember for now. Okay, for now you should remember that much of information. But in the coming sessions, we will discuss more, or you can say we will discuss more about the dipole. But for now, I am telling you, you just go through the electric dipole properly, because that is all formula is going to become. Because just remember one statement for now, that is, there is a magnetic dipole, magnetic dipole is same as electric dipole. If someone has covered the magnetic dipole very detailed and have learned from me, I am giving you a guarantee that you won't have any problem in the magnetic dipole. Okay, so that is a simple thing. But for now, you just remember all these details. We will discuss this in a later sessions. Okay, so let us proceed further. Our very important topic, that is properties of magnetic field lines. I hope you have revised all the properties of electric field lines. Okay, so properties of magnetic field lines. So let us start with the first. We will revise the electric field lines property. Do you know what is the first property of electric field lines? What is the first property? Tell me what is the first property. Who will tell me the first property of electric field line? What is the first property of electric field line? What is the first property? Electric field lines always originate from a positive charge and goes to infinity. That is the first property, correct? That is the first property. But in and electric field lines always originate from the positive charge and go to infinity. Clear? In the magnet case, the electric field lines originate from the north pole and goes to the south pole, outside the magnet. Remember that it is outside the magnet. So first property is that the magnetic field lines, I'm writing like this, okay? The magnetic field lines, okay, originate from south pole, sorry, from north pole and go to south pole. But remember this, there is a condition, it is outside the magnet, okay, not inside, it is outside the magnet. Remember the condition, it is outside the magnet, correct? That is a condition. So if I want to draw also, you can see how it is like look like. So let me draw it. So suppose this is my north pole and this is my south pole, okay, this is north pole and this is south pole. So magnetic field lines will come from here and enter like this, okay, magnetic field lines will come from here and enter like this. I'm not showing inside because now I'm talking for outside, so it will be something like this. Remember, they don't intersect with each other, okay, they never intersect each other. That we will also discuss one of the property, but for now you just remember like this, okay. That is the first property. I hope it is clear to you. Clear? Okay, what is the next property? Let us talk about the next property, okay. This is the first property, an example for this. Clear? Now next property is very simple. Wait a minute. Okay, next property is the magnetic field lines. Just give me a 1 minute. The magnetic field lines, sorry, the magnetic field lines originate, sorry, the magnetic field lines go from south pole to north pole, but it is inside the magnet. It is inside the magnet, okay. This is going to be happen inside the magnet, it is not outside the magnet. Clear? So now next property we can say is what? That it is inside the magnet. Clear? So if suppose we have a magnet and we're talking about the property, so this is north pole, this is south pole, and the magnetic field lines will go like this, sorry, and this is the magnetic field lines. This is for outside, it is north to south, but from inside it is south to north, like this, okay, south to north, like this, inside. Clear? These are the two properties. Now what is the next property? What is the next property? Can you tell me? What is the next property? What should be the next property of the magnetic? If you remember the electric field line property, you can obviously tell. You can obviously tell. In the next property, in electric field lines, the tangent on any curve, any electric field lines will give the direction of a net magnetic field at that point. I told you this property. So similarly here also, the tangent on the curve of magnetic field lines give the direction of net magnetic field at that point. Correct? So suppose we have a curve and at this point I am drawing a tangent. Don't look like a tangent, sorry. Suppose I am drawing some tangent. So at this point, if I ask you, this is my B net at this point, at point P. Clear? So this is the third property. Any doubt? Okay, let's move to the fourth property. Till here, anyone have a doubt? Now, what is the next property in electrostat we have discussed? That is the two electric field lines cannot intersect each other. Similarly, here also, the two magnetic field lines, third property, the two magnetic field lines, the two magnetic field lines never intersect, never intersect each other. Okay, what is the reason? You know, at a one point we will have a two direction of magnetic field, not magnetic force, because the direction of force and direction of magnetic field is not same. So remember, because at the point of intersection there are the two direction of a magnetic field, so that is not possible, so that's why they never intersect each other. So remember that this is not possible. If suppose I have a one magnetic field lines and this is another magnetic field line, they cannot intersect at this point. This is not possible. This is wrong. Okay, this is not possible. Not possible. Suppose this is B1 and this is B2. So that is not possible. Clear? Any doubt? Okay. Next property is what? What is the next property? I think you haven't revised the property of electric field lines. What is the next property? Next property we have told that the point at which the electric field lines are more, okay, that point will have a stronger electric field. Similarly here also, you can say magnetic field strength is directly proportional to the density of the lines. Density of the lines, that is what we have talked about in electric field also. Density of lines means, suppose we have a lines like this. This I have drawn there also. This is suppose point A and this is suppose point B. Okay, or some point X. So, and this is the magnetic field lines, correct? These are the magnetic field lines. And if I ask you magnetic field at A, or you can say A is greater than magnetic field at point X, correct? Why? Because the lines are more denser at this point, correct? Okay. Second property, there is one more property is there regarding electric field. What is another property regarding electric field we have discussed? That is, electric field lines will never form a closed loop. Electric field lines will never form a closed loop, correct? That is the one property we have discussed. Electric field lines we have never form a closed loop. But now we are discussing the magnetic field. Okay, so will magnetic field lines form a closed loop? Answer is yes. Magnetic field lines always exist in a closed loop only. If there is a magnetic field lines, then there must have a closed loop. Okay, so magnetic field lines always exist in a closed loop. That is a rule for a magnetic field line. It will always exist in a closed loop. So let us, if I ask you, basically what I am trying to say, if you see the bar magnet, okay, if you see the bar magnet, I have taken the example also, if you are able to understand. See, I have told you that is the magnetic field lines is from north to south, correct na? Suppose one, I am not drawing large number of lines, I am just drawing the two lines so that it will be clear to you, the diagram is clear to you. So suppose these are the two lines are going and it is like this, correct? This is like this. So can you see properly? If you see properly, this is forming a closed loop na? It is something like this, yes or no? So that is what I am trying to say. Magnetic field lines always form a closed loop. Why? Because it is not a conservative force. That means it is not a conservative force. That is why it is not a conservative force. Okay, it's form a closed loop. Here any doubt? Till here any doubt? So these are the some important properties of a magnetic field lines. There are the some more properties are also there, but by using this property you can solve a lot of, you can solve all the question almost. Okay, so there is no need of going for other properties. I am telling you, if you remember this number of properties, that is more than enough. Okay, now let us draw the magnetic field lines due to the different geometries. Some famous geometries we will draw. Okay, so first we will talk about the magnetic field lines examples. So some famous examples we will take so that you will get the idea for understanding. So let us first talk about a one bar magnet. Okay, how the magnetic field lines for a bar magnet look like, exactly how it is look like. Okay, then let's take for a circular ring. Okay, let's take for a circular ring. Okay, and what else we can take for a wire, for an infinite long wire, or any wire. Basically for a wire we can talk for a wire also. Anything else? Anything else? Anything else you think that is required? See, for this, basically, how will you draw? Basically, this is our north pole, this is our south pole, so our magnetic field lines will be like this. Wait. It's very difficult to draw. Okay, like this. Maybe my one has intersect with each others, but it reality don't intersect. Okay, just draw it properly. I am not able to draw it properly. Okay, this is our north and this is our south. Okay, for this is the axis, and suppose the current is like this. Okay, how will you draw? See, I at this point I, so it is something like this. Okay, okay, so it is something like this. See, this current will go in, outside, so it is like this, and this current will go inside, so it is something like this. Okay, now in wire, suppose the current is like this, so what you will do, I then curl like this, you will have a magnetic field lines like this. That is concentric circles. You can say it is like a concentric circles. Okay, it is like a concentric circles. So these are the some of the examples which you can refer for drawing the magnetic field lines. Okay, which you can use it. Yeah, I think I put the arrow wrong. Okay, no issue. Make it like this. Yes, now it is correct. So these are the some examples. Okay, this is my circular ring, this is wire, this is a bar magnet, this is what we have discussed. So these are the magnetic field lines due to the different shapes. Clear? Any doubt till here? So what are the properties? Just go through it once. I am showing you. Okay, then we will proceed further. Just go through these properties once. Then completed. Shall we proceed? Okay. Just give me 1 minute. Okay. Now our next discussion is a very important and very you can say very important topic for the NEET students. Okay, that is solenoid. Okay, forgive me if I am wrong with the spellings. Okay, I am not very much good with the spellings, so if it I am writing wrong, just leave it. Okay, because not we are not in the English class, we are in the physics class. Okay, so let us, can we start? Okay, so what is solenoid basically? First, see, solenoid is nothing but you take a one insulating color, basically one conductor or any insulating conductor or something like that. Or basically, what I'm trying to say, you have to take a conductor. Okay, just take a one conductor. Suppose you take a copper. Okay, you take a conductor, a cylinder of copper. Okay, and you have just take the wires and just revolved that, warped that wire, or you can say you have put a turns on the wire on that conductor, on copper wire, on copper conductor. That is called as a solenoid. That is simply a solenoid means. If someone asks you what is a solenoid, it is nothing, just what you do, you just simply take a conductor. Okay, some conductors, anything you can take, it's not necessary you have to take particular type of conductor. No, you can take any conductor and just put a wires around it. Okay, just put a wires around it. That is simply form a what, a solenoid. This will simply act as a solenoid. Okay, that will be simply act as a solenoid only. Okay, that is a solenoid. What happened? Yeah, that is simply a act as a solenoid. Okay, okay, so that will be simply act as a solenoid. What I am trying to say you, just put the wires around it. Okay, my simple thing is that you just put the, you just put the wires around it. That is what I am trying to say. Okay, let me draw it properly, otherwise you won't understand even what is my, what I am drawing. Okay, so just give me 1 minute to draw it properly. I can show you in the diagram also, but it is better if I draw, then you will understand it better. Okay, my drawing is not very much good. You will get a feel how it is going exactly. Because see, and in physics it is very important you feel the you feel it, each and everything, then you are able to understand. Okay, it is something like this. Clear? Yeah, it is something like this. I hope now you got the idea how it is going like this. Clear? Okay, this is not perfect. Yeah, clear now. So basically the current is, okay, so it is, it is a called as a solenoid basically. So if you see this solenoid properly, what you are able to think like, it is look like you have taken a multiples infinite number of what, a circular coils or a circular ring, and you just put them together, like you stack them together. I have taken a one circular ring, put another circular ring, and it will form a solenoid. It is like look like that, correct? Our aim is to basically what, to calculate the magnetic field due to this. Okay, so let us see first, try to see this first. We will see the cross sectional view of this. Okay, so let us see first, try to see the cross sectional view. See, we have to understand this, very important, it's very important. See, practical solenoid is very much important for JEE advanced point of view, and ideal solenoid is very important for the NEET point of view, and for JEE it is both for JEE means both are important. Okay, so cross sectional view, if we will see, okay, if you will see, what you will find in the cross sectional view, that there are the two things are there. Okay, in the cross sectional view, let me draw the cross sectional view, just give me 1 minute. Okay, this is a little lengthy topic, just you have to be patient in this. Okay, so if you will see the from here that I am drawing dots. Dot means the current is coming outside, correct? I am drawing a dots. Basically, cross sectional view means I have cut it like this. In the middle, I have cut it like this. Okay, that is a cross sectional view. And here we have a cross, means the current is going inside. Cross means the current is going inside, and this is our axis. Suppose this is our axis. Okay, now our aim is to calculate the magnetic field. How will you do? What is the approach? Let us see. And there is something, one thing is defined, something called as a number of turns. Okay, number of a small length, that is defined as a total number of turn per unit length. Total number of turns per unit length. Okay, just remember this, because it is used to come into the picture, so just you remember this. Okay, clear? Till here, anyone have a doubt? Please let me know, because now this is very important to understand. Suppose I have taken some point, let us say some point here. Okay, some point here I have taken like this. Okay, I can take anywhere, but I have taken here. I can take anywhere, it's not necessary to take here only, sir. You can take anywhere, no issue. And suppose I am going to this point, and then I am going to this point. Okay, correct? Suppose this angle I have defined as theta 2, and I have defined another angle in theta 1, and see, both the angle are taken in same sense, they are not in opposite sense, correct? And what I have did from a distance, from this distance x, I have gone and cut a small ring. This will be a small ring only, because I am drawing a cross sectional view, so it may be look like a strip, but it is a small ring. Okay, dx, thickness is dx, correct? Any doubt? Any doubt is there? What is the number of turn in this? Can you tell me what is the number of turn in this? What is the number of turns? The number of turns per unit length is there, na? So the number of turns in this will be, number of turns will be n dx. Okay, now our aim is to find the magnetic field at this point P. How will you see? See, if you try to see what we have did, we have cut a small ring from here. Okay, and from this ring, at this point, the ring, we are calculating the magnetic field at the axis, correct? This is a small ring, and at the axis we want to calculate the magnetic field. So what we will do, we will write dB is equal to integration, that is a net magnetic field, or you can say a better write like that, directly like this, that is B net integration, how much? Mu naught I, what is the radius? What is the radius? Mu naught I r square. Suppose the radius is r, no issue. Let us take the radius is r, so r square divided by 2 times of, what is the radius? R square, sorry, I think we are doing something wrong. The radius is not r, na, because radius is not given. Okay, no, radius is not r. Okay, let me write the first formula for you, that is r square, then x square, then we will figure out the things. Power 3 by 2. Anything else is left? What is the what is the number of turns? Yeah, the number of turns, because if you see this formula, this is for single turn. If suppose there are n number of turns are there, n number of turns, suppose the number of turns is n, number of turns, then what you have to do, you have to simply multiply it by this n. Okay, simply multiply b net is equal to, okay, just simply multiply it with n. Okay, that you can do everywhere, in any case, in any formula. Okay, this is valid for every formula, it doesn't matter. So here how many turns are there? N dx. Now you tell me what is the value of r, what is the radius? See, this distance is x. Okay, I want to know the value of r. How will you calculate? What you will do? Just tell me, because I want to know the approach. What is the approach you will do to calculate this x? See, one element I have taken like this. I can take one more element like this now. I can go like this. This is my element. From an angle theta, I am taking a small, this is called d theta. Okay, correct. So now you tell me what is the value of r. Now you tell me what is the value of r. First you tell me what is tan theta, or do by yourself. First you tell me what is the value of r. My question is very simple. You tell me what is the value of r. Okay, radius must be there. Suppose this radius is r. Okay, you tell me what is the value of x. See, I can write one thing now. Tan theta is equal to p by b. What is p? P is r, x. So x is equal to r cot theta. What is dx then? Dx is equal to, sir, minus r cosec square theta. Cosec square theta d theta. Any doubt till here? Okay, now you tell me. Okay, no issue, just put this value here. This will be mu naught I into r square into n. What is this value? Minus r cosec square theta d theta into, just let me make this thing little. Sorry. Okay, d theta, this is 2 times of. Now you will put this value here, so r square will come outside, this will become r cube. And one more thing, 1 plus cot square theta is cosec square theta. Cos square theta means cosec cube theta. Okay, now you just cancel out these things. This will cancel out again. Okay, 1 cosec theta will left, that will go above, and it will become how much? Sin theta. So mu naught, how much you will get? I into n divided by 2. Any doubt? And you will get integration minus cos, sorry, not cos, it's minus sin theta d theta. Now you tell me the value of theta. From where to where we have to integrate? From where to where we have to integrate? See, both are in the same. So theta 1 to theta 2. This you will get mu naught I n divided by 2. I will give you the conclusion, don't take stress. So this is cos, integration is cos theta. So cos theta, I have done everything correct or not? Let me check. Sorry, it will be from theta 2 to theta 1. Sorry, not theta 1. Well, first is coming theta 2. This integration will be from theta 2 to theta 1. Okay, so this will come to integration of sine theta is how much? Cos theta minus cos theta. So this will become cos theta 1 minus cos theta 2. This what we have discussed is called as a practical solenoid. Okay, practical solenoid. This is the discussion for the practical solenoid. Okay, and this is the value of magnetic field we have got. So how you have to remember, what you have to remember, let's go to the next page, and what you have to remember, just let me tell you, or it is better to tell it here only, because then you will remember the things in more better way. Let me just do little concise, all the things little concise. Correct? Okay. What I am trying to say, you have to simply remember what? Conclusion. This is a conclusion for practical solenoid. Okay. What is practical solenoid? What is ideal solenoid? That we will see in the next session. Just for right now, you just remember for practical solenoid. Spelling is a very big problem for me. Okay. Solenoid. Simply you remember this diagram. If there is a solenoid, okay, and there is a some point, and this angle is defined as, and this is my axis, this angle is theta 2, this complete angle is theta 1, then my magnetic field will be how much? Mu naught n I divided by 2 into cos theta 1 minus cos theta 2. Clear? What is the direction? Just curl your finger in the direction of current. Suppose the current is like this, just curl your finger, and there, by that you can know the direction of current. That is not important, but for now you just remember practical solenoid. What is a practical, what is ideal, that we will discuss further in the next session and more detail. It is, solenoid is not finished. We have just did the derivation, when we have calculated the formula. It is a general formula, but we will see it later more on this, and we will finalize that what is exactly the thing is about. Okay, just for now you just remember, for a practical solenoid the magnetic field is mu naught n I by 2 into cos theta 1 minus cos theta 2. I will teach you solenoid in such a way, no one has teach like that. Okay, it will be in very detail and every point will be clear. Till then, if you have liked this session, please like it, share it, subscribe it, and I hope your preparation is going on very good. I have bring a series of challenge questions for you. Just go and see that challenge question. I hope it will help you in your preparation also. Till then, take care, goodbye, have a nice day.